We've recently launched this white paper called Empowering Large-Scale Quantum Circuit Development, Effective Simulation of Sycamore Circuits, where we take a close look at the circuits that Google published as a part of their 2019 quantum supremacy paper, and we show what it looks like when you run those through the quantum ring simulator.
If you're a longtime listener, you've probably heard we can't simulate more than 50 qubits on a classical computer. Each qubit doubles the required system resources, and state vector simulation hits a wall, even on supercomputers. But what if there was a way to break this barrier on a laptop? Find out how tensor networks may be taking us into new realms of practical quantum computing for everyone in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the co-founder and CEO of Quantum Rings, and they have a pretty cool logo. You have to check it out. Bob Wold, welcome to the show.
Hey, thanks, Konstantinos, and thank you for the compliment on the logo. I'll pass that along.
Yeah. Bob and I got to talk a couple of times at events that were being run by Chicago Quantum Exchange. So I've been trying to get him on the show, and I wanted to get him on around the time where a certain paper is coming out, and we'll get to that. But first of all, maybe just share with the audience what Quantum Rings is.
First, thanks for having me on the show. Yeah, we met when you were giving a presentation at a post-quantum cryptography event in Chicago, and I remember almost sweating through my suit. And so here I am now in Colorado, wearing a hoodie because it's chilly outside. So yeah, it's good that we finally connected. Yeah, so Quantum Rings builds developer tools that make quantum computing accessible to everybody today. And we started by building a quantum simulator that can simulate some of the biggest and most complex quantum circuits on really small computers. So because our mission is around developer enablement and getting more developers into the quantum space, we've done all of our benchmarking by limiting our computers to 32 gigabytes of RAM. And so for those that are big into quantum simulation, they sort of know that if you use some of the traditional approaches, 32 gigabytes of RAM doesn't actually go too far. What we're able to do, though, is actually simulate essentially the biggest quantum circuits that have been published on, really small compute. I'm really excited about it.
Yeah, and the idea is that it's an SDK, right? So there's something going on in the front end on your laptop, let's say you, the users, and there's a whole lot of secret sauce going on in the back end.
Yeah. Well, so actually, I think thinking about that cloud model, so it is installed as an SDK. You just pip install it. Pip is the package manager for Python for people that aren't super geeks. And then it installs this, library onto your computer. The SDK, it does phone home real quick. It hits our servers and it's like, hey, I'm out here and I'm about to execute a big circuit. But then it does all that computation just on your constrained compute environment. And then gives you kind of the result as if it had been executed on a quantum computer. And so, essentially, while a quantum computer will do things using physics, which is way faster than a CPU can do things, we faithfully execute using all of those quantum physics characteristics that quantum computers are relying on to create their power. Okay,
so it really is done then technically locally.
Yeah, that's right. In fact, my cumulative AWS bill to date is less than $1,000 total. I'm just running a little database server. Yeah.
Oh wow! So it's just some kind of yes, you're allowed to proceed kind of.
That's exactly right. Yeah. In fact, you being a security oriented quantum podcast, probably sort of are well aware of the risks of having the ability to execute giant quantum circuits without having some sort of, phone home and make sure I'm allowed to do it. Mm-hmm. And so a huge part of the interaction between client and server on this is really just to check in to see what you're allowed to do. And so it checks in and says, hi, I'm, Bob at Quantum Rings. What am I allowed to do? And it says, hey, you're registered to execute up to 100 qubits of simulation. Right. And then it executes locally. We also do have, because of ITAR restrictions, which is the US government's, who you are and aren't allowed to ship things to. We do make you answer a couple questions when you register too about just where you're coming from and, who you are.
Yeah, we talked about the whole quantum export thing a few times and how it's like the crypto wars all over again.
Totally.
I don't know how long that's going to last. Other countries are going to surpass us, I'm sure, in some ways anyway. So basically, you've already said something that should be flagging alert bells in listeners' ears. So you said 100 qubits, and we're talking about running on someone's laptop.
Yeah.
This is sort of just not possible according to everything we've known up to this point. So I definitely wanted to have you on to get into this. So you're not just using a normal quantum emulation scheme. You're doing something a little different. And I believe it touches on something that is kind of near and dear to my heart. And I'll let you dive into the world of tensor networks for a moment here.
Yeah. Well, we won't spend too much time on it because it's kind of like a slippery slope. But basically, okay, so if you talk to somebody in quantum and you tell them you just heard a podcast and some guy was saying he could simulate 100 qubits on a developer-sized laptop computer, they'll probably think you're crazy. Now, that's because up until a couple of years ago, the type of simulator that was used was this thing called a state vector simulator. So a state vector simulator, it essentially simulates like perfect. Like, okay, so zooming out even further, a quantum computer, we talk about these things having qubits. We said this has 100 qubits. 100 qubits are essentially the equivalent of like 100 bits in regular computers, but instead of holding a 1 or a 0, they hold this like complicated state of maybe being a 1 or maybe being a 0 that's like interconnected with all the other qubits that you have. That's sort of, you could have a whole episode on just how that all works, right? And so the way you simulate that is by having these giant matrices of like all of the quantum state, they call it, that's associated with this thing. And so a state vector takes 2 to the n bytes of memory, or if it's double precision, 2 to the n times 2 bytes of memory for every qubit that you take up. And that's, so like you can simulate like a 32 qubit system, but like you can't simulate a 40 qubit system without a supercomputer. And so then to say I'm doing 100, that sounds totally impossible. But actually, about a year and a half ago, these tensor networks for quantum simulation started getting a little bit of momentum. And so the idea is that like if you change the underlying data representation to tensor networks, which the world kind of popularized with artificial intelligence, you can actually store quantum state with some level of approximation in a much smaller memory footprint. And so there are other tensor network simulators on the market. But Quantum Rings has a novel approach to use tensor networks with some really kind of intelligent approximation so that we can sort of hold a much better level of accuracy while still letting you scale up really, really big behind the scenes.
Right? Yeah, because somehow it felt before this point like the universe was protecting itself. 50 qubits were the limit. And then when you did it with tensor networks, oh my God, how am I going to do a contraction on this mess? And how am I going to get it to give me an answer? So it still felt like 50 qubits was about the limit,
Yeah.
So you've come up with some other creative way.
Yeah. And what you're talking about there when you said the limit is like, basically like the wall that stands between like quantum advantage, right? Like it's like the problems that are not solvable and the problems that are solvable by classical computers. And one of the like crazy things is that we've seen really cool papers come out that have claimed quantum advantage, but over time, as quantum computers get better and better, like more and more innovation comes into the space, which then means that like quantum-inspired classical algorithms get better and better, or quantum, the ability to simulate quantum computers on classical hardware gets better and better. And so like that line of like, what is quantum advantage is actually moving because the better quantum computers get, the better the rest of us get in the classical space also, right?
So we're in a wonderful nexus here where we're dealing with the idea of quantum advantage, the idea of quantum-inspired, enabling quantum simulation in a different way to get us past that point of quantum. It's kind of amazing that all these technologies kind of get together. And I've hinted over time that I thought they should all kind of get together, but here they are. So this is, of course, closed source and protected, but you have the SDK and the ability to write your circuits and execute them locally, as we said. So if someone runs this, what are they really doing? Are they learning a new language from scratch? Are they building on anything that they already know, let's say with Qiskit?
Yeah. Well, I can't remember if we talked about this in one of our previous conversations, but you queued it up perfectly. So yeah, Qiskit's like a super popular language for people that are developing for quantum computers. And the Quantum Rings SDK is totally Qiskit compatible. And so you can just write in the language that you're comfortable with. If you want to take advantage of some of the like Quantum Rings extra secret sauce, like at the programming language, you can change your imports to import from Quantum Rings instead of importing from Qiskit. But you can also just like literally leave it importing from Qiskit and just run Quantum Rings as a Qiskit backend. Mm-hmm. And so, yeah, you can, whatever algorithms you've been working on, you can just simulate them bigger and with higher fidelity by registering for a free account at Quantum Rings and running your simulator. Now, one of the crazy things though, so you're spot on. There's this huge challenge as a startup because like this community, the whole quantum community is like in this pre-competitive state, where like a lot of the information that's going out is being very like open in the interest of trying to like iterate on each other's work and build things better. As a startup, we have a closed source simulator and we actually, try to keep pretty close to the chest, the real secret sauce and how we're doing it. But we need people to also like know that it's good. It's giving a quality result. And so that creates this, like, I call it this credibility hurdle that we have to get over, where we show people that, hey, we're not just running these really large, multi-hundred qubit circuits with millions of operations, full entanglement, but we're actually executing them faithfully. And so one of the things, we've recently done is launched this white paper on Archive called Empowering Large-Scale Quantum Circuit Development, Effective Simulation of Sycamore Circuits, where we take a close look at the circuits that Google published as a part of their 2019 quantum supremacy paper. And we show what it looks like when you run those through the quantum ring simulator.
Yeah, that's a good approach, because that was the first paper that really, you could say, generated the biggest buzz, right? So now you're showing that you can easily simulate that.
Well, not easily, but it's easy for the end user. It's pretty hard.
Yeah, the sarcasm is lost in a podcast. Now,
but you're spot on. Yeah, so essentially, so in Qiskit, they have this class called quantum circuit. Mm-hmm. So you can essentially import, like, normally you compose circuits in Qiskit, but you can also say like quantum circuit dot from QASM and then pass it a QASM file. So one of the cool things that Google did with their quantum supremacy paper is they had this like really rich data room attached to it, where they published all of the QASM files. That's like the end file that you hand from whatever language you're developing into the quantum computer. They published all of them. So you can just go and download them, import them into quantum rings using one line of code, and then execute them. And then, so depending on what size you bring, if you import the smallest circuit that they published, which was like a 12 qubit circuit, it'll actually just run on a really small computer. You could even run it on Google Colab, and it'll execute really quickly. In fact, you can run all the way up to about their 40 qubit circuits, even on a Google Colab environment, before you start running into some RAM restrictions that make you need to go to a slightly bigger environment. But then you can run even their biggest 53 qubit circuit. And by the way, they publish lots of varieties of these qubit circuits, but you can go to the very most complicated one and run it. It takes about 2.5 days on an Intel i9 with 32 gigabytes of RAM. But executes completely. And what's even more exciting than like just executing them is the quality of the execution. So one of the things that Google did that's like super exciting in their paper is that they didn't just like make a really big circuit that would be really hard to execute. They executed this thing, and they provided a methodology for quantifying the quality of the execution. Mm-hmm. So they call it, all right, we're going to get a little nerdy here for a second.
No, that's fine. That's great.
They call this thing the linear cross entropy benchmark. They call it the XEB as kind of a 3-letter acronym, because we like 3-letter acronyms in this field. But basically that measures how the output values from these random circuits measures up against what the distribution should be, given the quantum state that was encoded into your quantum circuit. And so you can score basically between a 0 and a 1, where a 0 would mean that, you got output, but it has no correlation to like what the output actually should have been, all the way up to 1 where it's like the hand of God itself reached out and changed physics and made it, an exact perfect, distribution, right? And in their experiment, when you start off with a really small circuit, you start off with a pretty like reasonably high cross entropy benchmark. I think it starts off in like the about a 0.3. And then over time, as the circuit size increases, both in terms of number of qubits, but also in terms of number of operations, the noise that you have in the system and the errors compound, and you end up with a lower and lower cross entropy benchmark. In their paper, they finished it with a cross entropy benchmark of 0.002, which is, greater than 0. So very exciting. In our paper, using the same methodology, we start at about, 0.6, between a 0.6 and a 0.7. And, quite impressively managed to sort of hold that level as you increase the circuit size all the way up to their biggest and most complex circuit, which, to be frank, is a result that we had to sort of triple check because it was even, more impressive than we probably expected going into it.
Yeah, in some ways that's mind-blowing, and in some ways it makes you think of what even the earliest simulations were. They were always kind of like perfect qubits. Right?
Yeah.
And that created a problem. You had to introduce noise. You had to do all this just to get like a realistic result.
Yeah.
But yeah, no, that's impressive because we're entering these like more real world qubit numbers. And you mentioned 40 qubits as one of the levels, and that's where you stop being able to do this for free, right? If you want to use this SDK.
Oh, yeah. Great question. So that goes into our monetization policy. So right now, for students in academia, we have 100 qubits of simulation for free.
Okay.
There's a very strong chance that we're bumping that up to 128 qubits for free by the time this podcast airs.
It's so crazy. Like, it's bonkers. Like, for free, you're doing something that shouldn't even remotely be possible. Okay.
Totally. Cool. Now, if you sign up for the starter package, which is free, you get that 128 qubit level for 30 days. That way you can run any kind of experiments you want in the first 30 days. And then, get this, we downgrade you to 64 qubits.
Oh, wow. Okay. Well, that's atrocious.
So the, the hope is like, we really think like in any industry, once you've brought the developer tools and you've made things like really easy for anybody to come in and play in that space, that's when things really start to explode. Mm-hmm. And, we've sort of recognized this shift that's happened since NIST's post-quantum cryptography standards have gone out, where a lot of people have changed their mindset from, quantum computing is some cute sciencey thing that people in lab coats are doing, into something where it's like, wait a minute, my IT guy is telling me I have to have like a post-quantum cryptography strategy. Like, this stuff is coming at me. How do I start building up a capability now? And, I think the people that are in reaction mode will react a little bit late, but the people that are kind of in proactive mode, where they like to see the opportunity in chaos, they look at this and say, like, how can I position myself to be a leader in kind of a post-quantum world? And that's where we want to help.
So I'm hearing a few things here, and I have to like connect the dots for a minute for listeners to wrap their heads around this. So you've got these limits that there's that phone home to check. Who are you? What are you allowed to run? Okay. And you're running on a laptop that you said could take 2 days to run one of these bigger experiments.
That's right.
So there's this paper that people could see in the show notes. If you start to put all these pieces together, and you mentioned post-quantum cryptography, that was a laptop example.
Yeah.
What if there was some kind of tier of service where you phone home and it says, oh, you're running Oak Ridge and you're allowed to do 4,000 qubits that are perfect. Here you go, have at it. What happens then? I mean, are these artificial limits being put just so someone doesn't run their machine for a year? Is there a limit? Can we do the impossible here with something like this if you were allowed it to run on beefier hardware?
So, I mean, there's like a short-term answer and a longer-term answer. And the longer-term answer is like, probably you can do anything, right? With, but okay,
terrifying.
But
terrifying. Like, I know that's funny and everything, but like, okay, that's super freaky. I want people to think about that for a minute.
But shorter term. Okay, so right now, some quantum simulators have started creating the ability to scale horizontally. Like, so in the classical computer science world, we've always talked about like horizontal scale and vertical scale. So vertical scale being like, I just put a bigger and bigger single computer to do more and more processing of the thing. And then horizontal scale is like, I can split the problem up and share it across lots of different computers and get it done faster that way. So one of the ways that like the Oak Ridges of the world are so powerful in terms of like how many petaflops they can calculate is that they have like, 20,000 single blades, they call them, right? Mm-hmm. Now, I'm pulling 20,000 out of thin air. I have no idea how many blades they have. They have lots of them. And then those blades themselves will also be like very capable, very beefy machine with potentially terabytes of memory, potentially GPUs. A lot of times they'll have sort of like different computers sort of like arranged in this giant data center, and you can get access to what you need. Okay, quantum rings can scale vertically today. So if you get one single node with a huge amount of RAM and a huge amount of processor, you should be able to take on bigger and bigger problems. Again, it's not going to happen as fast as a quantum computer can do it, but you should be able to execute very large quantum circuits. Once you hit the limit of what a single node is capable of, we have not begun getting into scaling horizontally. Right. And so there is like you're going to hit a wall in terms of the number of qubits that you can simulate. And we have not experimented with like pushing that limit to understand exactly what the bottlenecks are. But from a RAM perspective, I think you could imagine like potentially like somewhere between 1,000 to 2,000 qubits would be capable of being represented in the data structures in RAM using the approaches that we have. But then how much compute time does it take to actually do the processing behind it? We would need to explore that in great detail before we sort of said, hey, don't worry, we can do 1,000 qubit simulation, right?
Yeah. How does that scaling look? Is it like a logarithmic nightmare that occurs? Or do 2 days become 2,000 years?
Yeah. And that's kind of one of the like hardest things about simulating quantum circuits is that like none of them are the same. So we talked about this Google Sycamore. Their circuits are so cool. They're these monsters. They're like intentionally designed to be like hard to simulate. Like I think that is actually the point. Like that's probably like one of the top 5 priorities, right? And so they'll do this like super far field entanglement with like, complex operations. And so even though they're like 53 qubits and maybe, 25,000 operations, something like that, they are super hard to simulate and they take a huge amount of CPU time. At the same time, we've seen circuits north of 200 qubits executed with our simulation tech, and they can execute a lot faster if they have like much more reasonable kinds of entanglement, like near field entanglement, or in the event that like you're doing single, like if you could do as many single gate operations as you want, and that's going to be easy.
Wow. So if I'm hearing this correctly, it's possible that with hardware that exists right now, you could be outperforming some of the logical machines expected in 3 years.
It depends on what your performance characteristics are. So I would say like from a speed perspective, never, not even close.
Okay.
And now from a like quality perspective, it probably depends a lot on the roadmaps that they have, right? Mm-hmm. Like, what is the definition of a logical qubit? What kind of fidelity does it have to have? And so like, I wouldn't want to rush there. But what I would say is that like, if you want to take advantage of those types of systems that are going to become available, that are going to be able to execute quantum circuits like that, you're going to need to build very large algorithms. You're going to need to integrate those algorithms into the rest of your like R&D system. Like if you're a pharmaceutical company and you have this desire to do like drug discovery using VQE, it's like, okay, how do I go from what the scientist is working on over here who doesn't know anything about quantum to like simulating this on a quantum machine? Well, you could start building all of that out today using simulation. And then when your, 200 logical qubit system comes out, you switch over to something like that. And then it goes, 100 times faster I don't think the aim is to take away the need for a quantum computer. The need is to like pave the road for really good quantum computers and to help companies get ready for it quicker. There is a chance. And like, the only reason I'm even going to say this is because the execution on the Sycamore circuit turned out to be so good. Like there is this idea that maybe in the universe of problems that are like unsolvable by computers using classical algorithms, that if you simulate quantum algorithms on a classical machine, maybe some of those become solvable faster. That's like conjecture, I would say, at best at this point. But I think that there is a real possibility that situations like that are discovered.
There was that Chinese paper everyone talked about, and they used, of course, D-Wave, and it was the whole kind of hybrid approach, farming out parts to classical machines and et cetera. And folks have dived into it, and it was like a 50-bit number. So obviously it's not the end of the world.
Yeah.
The difference between a 50-bit number and a 2048-bit number is like a 7-digit number and a 617-digit number. It's a pretty big difference.
Totally. Yeah.
But that said, every time one of these things happens, I wonder if we have the potential to learn something or open up some door, some new path that might come out. So you're kind of hinting that, who knows, there could be a paper in the future using one of these approaches that makes everyone go, wait a second, are we going to be factoring numbers a little sooner than we thought?
Yeah, I mean, so this industry is full of hype, and I don't want to be a generator. Totally. I don't want to be a generator of hype, but every industry always says that there's no way such and such is going to happen until all of a sudden it's happening. And then you're like, oh, well, I guess that is going to happen. Right. And I do think there's a very strong possibility that with the massive investment that's going into quantum around the world and kind of all the people coming from non-quantum into quantum because of that, I do think that there's a very strong chance that things that we're just not expecting happen, and they sort of provide a step function in terms of what the capabilities are. And I hope that is not done with Shor's algorithm or other factorization stuff first. The 50-bit problem that you were talking about, I think they used D-Wave, like you say. So it wouldn't have been done using Shor's algorithm. But I think the question we should really look at is it's not what was the size of it. It's not what was the size of the number that they factorized. It's sort of what could the trajectory of that be? And so to go from 50 to 52, is that something that's capable on this machine? Okay. Is that linear growth? Is that exponential growth? What does that look like? I'm not that nervous about it because I can literally in a Python script on my Mac, factorize a 50-bit integer,
of course.
But I think it's a really exciting thing to explore, because up until now we've been talking about Shor's, which requires, full large scale logical qubits on a utility quantum computer. If you can take an approach that looks at annealers, I think it's a cool idea. I like it.
Yeah. So potential terror in the industry. We'll see.
Totally.
As we're nearing the end of the year, it's fun to think along these lines.
Well, one of the really interesting things, I don't want to be the producer of any kind of hype, but for whatever reason, my Google newsfeed, it knows that I'm into quantum, and it's spot on about that. It thinks I'm into crypto, which is not really the case, but I can see from my Google searches why it thinks I'm probably into crypto. And I always get these things about mysterious like wallets that have been like,
Yep.
dormant for decades, and then all of a sudden they open up, and every once in a while you can kind of like somebody figured out the backstory of like who that was that unlocked this wallet that had been previously like totally inaccessible. But there is a lot of crypto out there that has been like permanently lost, or like semi-permanently lost. And so, yeah, I mean, like this isn't something I'd raise money on, but like if there was a startup out there with like a credible path to just like unlocking all of those wallets, I feel like you could probably get some interest.
I'll tell you why I disagree. Because once you admit that such a service exists, you will be unlocking wallets worth zero. Because no one will trust. Yeah, blockchain, that's it. Bitcoin's value will plummet.
Yeah.
So that would have to be a secret service.
Yeah, although on that note, that is going to be one of the really interesting things to see when it comes to like post-quantum cryptography is how it impacts blockchain and things that are built on top of blockchain. Because, there definitely was there was a lot of assumption that like this is unbreakable, therefore we can put it totally out in the open. And, I can definitely see that they're going to have like post-quantum Ethereum and post-quantum blockchain,
The original Satoshi Nakamoto paper, just within the first paragraph, boldly claims that, these types of calculations are not, reversible. And it's like, oh yeah, good luck with that. Yeah. Even when I read it, I knew that was a problem. Yeah. So this is amazing. And the best part is people get to try it, as you said. So I'm going to have show notes, a link to the paper, but also a link to the site, which lets people see if they qualify for the 128 qubits, I guess, at that time, or the 64. Just what you didn't think was possible, just 64.
That's right. Yeah. And, I'll give you a couple other links that are on the last page of the white paper, but just to make them available. So, the simulator itself is closed source. All of the source code to repeat this experiment, to go and grab all the files from Google, run them, do the analysis for people that want to, spend some time with their computer churning, is available on GitHub. And, we would love any input on this paper, whether that input is, this is amazing, this works, it's all, I'm going to change the world with my quantum algorithms, or whether it's, hey, here's something you overlooked. Let's take a closer look at this part. We'd love to invite the scrutiny to try to make sure that we can really provide tools that are really solid so developers can get here and start changing the world.
And if someone wants to spend more on cloud than you spend, are they allowed to run this on some crazy beefy instance and still do it, or will it be denied? Will it be told you can't?
Yeah. So our telemetry does tell us it keeps everything like very high level. We don't look at the circuit that you're executing, but we do take some basic information like what's your CPU size, how much RAM do you have, what's the host name. And so usually from those things, we can sort of tell if somebody's using it across a lot of different computers or if they're using it in the cloud or whatever. We don't have anything in our terms of service that say you can't use it in the cloud.
Okay.
It will limit you to the number of qubits that you have a license key for. But like even, ourselves, a lot of times we will take this and run this on other compute because you just don't want your computer sitting there churning at 100% CPU for like 2.5 days.
And it might heat bill. Execute faster. Is that possible?
On the cloud?
Yeah.
Yeah. So, so actually, it's a great point. So we got a whole bunch of free compute time from Arizona State University. So shout out to those guys. Thank you, Arizona State, for that. They have this thing, they call it their Soul supercomputer. It's like in their research computing group. So we, like I was describing when we were talking about Oak Ridge, they have lots of individual nodes that have varying different sizes, but you can actually like book whatever compute environment you want. So we would always only use 32 gigabytes of RAM as we use those computers. But we actually ran most of the experiment on their compute. Now we have run the hardest circuits on our own compute just to like make sure there's no, oops, we gave you too much compute or something. But they can run substantially faster as you have more and more cores, and you can get more and more cores on the cloud. So yeah, absolutely, you can accelerate this. Yeah.
If you're impatient, then it's your money. Awesome.
Yeah.
Yeah. Bob, thanks so much for finally coming on. excited to see how much of a stir this paper causes and see what people think when they start using the service.
Yeah, it's been an absolute pleasure. Thank you so much for having us on.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today in case things got too nerdy at times. Let's recap. While waiting for fault-tolerant quantum systems, developers looking to design and test circuits have relied on quantum state vector simulators. A powerful laptop would let you simulate about 35 qubits, and supercomputers would put you into the 40 to 50 qubit range. It was also possible to simulate more qubits than that using tensor networks, but the difficulty of contracting or doing all the dot operations to get an answer quickly choked systems. And we maintained the 50 qubit barrier because of fidelity loss. Quantum Rings has found a way to simulate hundreds of qubits and millions of gate operations while maintaining high fidelity. And you don't need an Oak Ridge supercomputer. You could run this on a laptop or cloud instance with 32 gigabytes of RAM. This means developers can now test circuits expected to run on tomorrow's quantum computers. Will tensor network approaches like this potentially affect cryptography? That's hard to say. The Quantum Rings team used their SDK to simulate Google's infamous 2019 quantum supremacy paper and published the results in a new paper linked in the show notes. It's possible to run this experiment yourself, but it'll take about 2.5 days. This is a crucial point. While the Quantum Rings SDK can break the state vector barrier we've been used to, actually executing the circuits takes much longer than we expect fault-tolerant systems to run the same code in the future. Quantum computers will take milliseconds instead of days. The Quantum Rings SDK is easy to use and is even compatible with Qiskit. It's closed source and phones home to ensure you're authorized to run, but the rest of the work happens locally and you have unlimited executions. You can get commercial accounts, but academic users can have free access to 128 qubits, and non-commercial users can get 64 qubits free. Check out the link in the show notes to get started. That does it for this episode. Thanks to Bob Wold for joining to discuss Quantum Rings. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.